Hello and welcome to the ZOOK Rupture Disk webinar. Rupture disks are safety devices designed to break reliably at precisely defined pressure levels. While modern rupture disks generally perform well, there are a variety of conditions and situations under which the integrity of rupture disks may become compromised and they won't operate as designed. When this happens, plant equipment, personnel, and the environment are put at risk. During this webinar, you will learn about the selection and sizing of rupture disk, along with techniques you can use to troubleshoot the operation of your disks to ensure they perform optimally. My name is Richard Clark. I am the Vice President of Business Development at ZOOK, and I will be your host today for this webinar. I would also like to introduce the presenters today, Ben Bow and Yip Wai Soon. Ben is the Regional Sales Manager at ZOOK Asia, and Yip is the Engineering Manager. I will now pass it over to our presenters to begin the webinar.
Thank you, Richard. Hello, everyone. My name is W.S. Yip, and I am delighted to be one of your presenters today. Thank you for taking time out of your busy day to join us online today.
Thank you, Yip. My name is Ben Bow. Some of you listening will know Yip or myself. I also want to thank each and every one of you who have taken the time to join us today. It's great to have you with us. Our goal today is to try and share some of our knowledge and to help you understand some of the basics and fundamental of a rupture disk device. We welcome your question, which you can ask online at any time on your screen. We will answer this in a Q&A session at the end of the webinar. In the event that we do not have enough time to respond during this session today, we will be following up with you individually after the webinar. So please ask your question anyway. Before we start to discuss what you need to know about selection, sizing, and troubleshooting, we want to provide a quick introduction to rupture disks. What is a rupture disk? First off, what is a rupture disk? A rupture disk is a safety device used in a pressure release system. It is a one-time use part using a calibrated thin diaphragm designed to rupture or burst at a designated pressure. Because of the many ways pressure systems are designed, the disks are also custom engineered to protect plant, personnel, and equipment from unplanned or unexpected overpressure. In short, the disk is designed and specified to prevent the dangerous effect of an uncontrolled overpressure situation. What does a rupture disk actually do? A rupture disk is a differential pressure device. A proper rupture disk assembly creates an impermeable barrier in a pressurized system, and it bursts or opens when the differential in pressure across it reaches a designated level. We have a quick video to show you demonstrating a rupture disk opening. Let's play the video now.
Here, you can see a rupture disk mounted to the end of a chamber, which is sealed at one end, and a rupture disk mounted on the other. Pressure is introduced into the chamber, and the disk bursts or opens when the pressure differential reaches a set point of the disk. Differential pressure simply means the pressure on one side of the disk is higher or lower than the other. If you pressurize both sides of the disk equally, nothing would actually happen. Here's another example using water. Rupture disks are custom designed safety devices. They can be engineered to function in both gas or liquid service, what we call compressible or incompressible service.
So you can see from the video, a compressed gas has far more stored energy than liquid, and the burst event is much more violent. In terms of rupture disk design, a gas burst poses significantly more challenges to the rupture disk engineers. A simple way to explain what a rupture disk is, it is an engineered weak spot in a pressurized system that ruptured at a designated pressure. Very similar to what a fuse does in an electrical system to prevent an unsafe condition.
Thank you, Ben. Rupture discs have been around for a long time and have earned an excellent reputation for successfully protecting all types of pressurized equipment. The original rupture disc was simply a piece of thin metal foil clamped between pipe flanges. As the internal pressure increases in the system, the foil, which is designed to be weaker than the vessel wall, would yield and eventually rupture to safely relieve the overpressure and protect the integrity of the system. It was a simple yet effective design. Subsequently, the first rupture disc device was developed and patented in 1931 by incorporating two additional features to improve functionality. A reusable holder was introduced, improving burst repeatability by holding the metal foil consistently and providing a better seal between both the disc and holder and flanges. The second improvement was to introduce pre-bulging of the disc foil to improve cycle resistance and reduce fatigue. The design is simple and fail-safe, relying on the tensile properties of the foil to control the bursting pressure. Since that first design, manufacturers worldwide have been working on new modern designs to address the demanding applications found in today's modern processes.
So what are the advantages of rupture discs and why use a rupture disc at all? Well, first and foremost, for safety and protection of personnel, plant, equipment, and the environment. Pressure and pressurized systems are all around us, and an overpressure situation can be extremely dangerous. We just saw two very small volume controlled demonstrations, but you can easily see the effect of the released energy in those small systems. Rupture discs are passive devices with no moving parts. They are extremely fast opening, typically going from closed to fully open in less than 3 milliseconds. Rupture discs provide a leak-tight seal and are available in a wide variety of corrosion-resistant materials. Since there are no moving parts, rupture discs are visually zero maintenance devices with very high reliability. They are a time-tested safety products. Therefore, rupture discs are a very effective low-cost solution to a pressure relief requirement. There is another method of pressure relief that most of you will be aware of, and that is a pressure relief valve, also known as a safety relief valve. A safety relief valve is typically a reclosing device. So why use a rupture disc instead of a relief valve? Let us look at costs. Comparatively speaking, rupture discs are very inexpensive compared to valves which have large housing and integral mechanicals, especially in larger sizes or when exotic materials of construction are required. Second is leak rate. Valves by their nature can leak, which can be a problem in some services. Rupture discs, however, are visually leak tight. They are basically a solid barrier with leak rates at the molecular level. The disc is very fast acting and unlike a relief valve, does not require a change of direction for flow to take place. There are no moving parts in the disc, so the reliability is high. There is no way to adjust the disc setting, which makes it tamper-proof also. Notwithstanding the benefit of the disc, there are many cases where a relief valve is actually the preferred method of pressure relief, and we are the first to acknowledge this. The most common would be in processing or continuous service application, where downtime is a problem. A valve will typically reclose after relief, whereas a rupture disc would need to be replaced prior to a restart. However, there is a way to get the benefit of both the disc and the valve by installing a rupture disc directly upstream of a safety relief valve. This is a very common application where a rupture disc is used to isolate and protect the valve from the process media. The inexpensive rupture disc is the only parts exposed to the process until an actual overpressure condition occurs. This is extremely advantageous in highly corrosive application, combining the advantages of a fast-acting leak-tight rupture disc below and the reclosing functionality of the valve above. Also, depending on the disc model, the valve can be tested in situ without the need of removal, thus saving significant downtime and costs. However, there are also related challenges when installing a rupture disc upstream of a safety valve. Because a rupture disc is a differential pressure relief device, pressure cannot be allowed to develop in the space between the disc and the valve devices, and hence a suitable telltale indicator should be installed to ensure pressure build-up downstream of the disc is detected and eliminated. With the addition of a rupture disc in the relieving system, the flow capacity will need to be considered, and we will address them when we touch on this sizing later on in the presentation. Rupture disc can also be used in parallel with relief valve. A relatively small relief valve can handle any low-level pressure relief requirements, and with the rupture disc to provide additional capacity for extreme requirement. For example, a fire case scenario. This saves the high cost of installing a large relief valve, which is not required for most relief cases.
As you can see, there are many different designs to choose from, which can be a challenge for engineers trying to select the best design for their application. In an effort to simplify the selection process, we will now build a family tree that groups similar designs. For this webinar, we are going to keep it simple and limit the discussion to widely manufactured designs and not custom hybrid designs. The first division is based on material, either metal or graphite. Metal designs are divided into forward-acting or reverse-acting. The common characteristic of forward-acting disc is that the foil, which the disc is made from, is placed in tension when exposed to the system pressure. Burst is initiated when the tensile strength of the foil is overcome by the system pressure. For this reason, they are also known as tension loaded. There are several designs of tension-loaded discs available to allow better cycle resistance, burst control, or limit disc fragmentation. The three most common designs are the pre-bulge, composite, and Scott forward-acting discs. On the contrary, the common characteristic of reverse-acting discs is that the disc foil is placed in compression instead of being stretched when exposed to the system pressure. To do this, the foil is first formed into a dome shape and installed with the system pressure acting on the convex side of the dome. Burst is initiated when the disc dome strength is overcome by the system pressure and collapses to open along scores in the foil or by shearings or knife blades. These discs are also known as compression-loaded or reverse buckling. Again, there are several variations of reverse-acting designs available that enable us to select different models across a wide pressure range, tighter burst control, or compressible or incompressible service. Ultra-low pressure discs are also available, capable of opening at pressures in the millibar range. It should be noted that compression loading of the disc allows the highest cycle life with operating pressure up to 95% of the disc minimum rated burst pressure without increasing fatigue and nuisance bursts. Extra care needs to be taken when selecting reverse-acting discs, as some designs are not fail-safe. Incorrect selection or installation can lead to a dangerous situation. Reverse-acting discs can be more vulnerable to damage and are specifically designed for either gas or liquid service. Graphite discs are made from a high carbon mix that is processed to produce a graphite. The first thing to know about graphite is that in its raw state, it is essentially a black carbon sponge with approximately 13% porosity. To remove the porosity and create impermeability, there are two processes undertaken by ZOOK. Resin impregnation is the first and most common process used. Various resins have been used over the years, but typically they are phenolic based. Through a process that includes pressure, vacuum, and temperature curing cycles, the graphite pores are filled with cured resin that renders the graphite material impervious and suitable to be used as a graphite rupture disc. Resin-impregnated graphite provides good corrosion resistance, inert material with non-ion contamination, temperature stability, and predictable results. Another process is a patented fluoropolymer sintered process. This involves preparing the graphite substrate to accept the fluoropolymer in the form of both liquid and powder. The coated graphite is then sintered at high temperatures that produces a highly bonded coating to the raw graphite, resulting in an impervious material. In addition to all the resin-impregnated graphite features, the fluoropolymer sintering process has greater corrosion resistance, allows higher operational temperatures, post-FDA approval, and has a non-stick finish. As you can see, selecting the best possible rupture disc design is not a simple task for any one person to tackle on their own. Good collaboration between the end user, system designer, and disc manufacturer is essential in getting it right the first time. Every application has both common and unique criteria that will guide the selection process. Common criteria include the following: vessel maximum allowable working pressure, disc burst pressure and temperature, normal system operating pressure, operating ratio, and burst tolerance.
I want to take a minute to point out that we often do product training and factory school for customers, channel partner, and employee. And this section of the training normally takes 4 to 6 hours. We could easily spend an entire day going over industry definition, rupture disc terms, and model, and the methodology for selecting rupture discs. For the purpose of this presentation, we will only be reviewing the key parameters. In Asia, the commonly adopted codes are namely North American ASME or the European Union Pressure Equipment Directive, EN ISO 4126-2. It is worth mentioning that this webinar is aimed at the European style specification relating to the Pressure Equipment Directive. If you would like to learn about the North America ASME standard based on the manufacturing range specification, that webinar is available on ZOOK website also. So let me now go into the definition to further elaborate the terms Gip just mentioned. Maximum allowable working pressure, or in short MAWP, is defined as the pressure limits of a vessel as determined by the manufacturer. If a rupture disc is used as the sole primary relieving device on a pressure vessel, the rupture disc burst pressures shall not be set greater than the MAWP. Choosing a burst pressure below or well below the MAWP is fine. However, this may affect the service life of the rupture disc when operating closer to the system operating pressure. As such, the MAWP forms the basis in the pressure setting and sizing of the rupture disc. So it should be noted that choosing a rupture disc burst pressure lower than the MAWP will result in a larger disc size during sizing calculation. Specified burst pressure is defined as the desired burst pressure of the disc. This information is normally provided by the customer or the end user. This is the pressure at which the disc is required to burst as specified by the end user. Typically, a process engineer determines the specified burst pressure in their overall system design calculations, and this requirement is provided to the disc manufacturer to manufacture the rupture disc. System operating pressure is the normal operating pressure range the disc will see in service. The disc maker needs to know this information to be able to choose the correct disc suitable for the application. For example, some basic discs cannot tolerate operating pressures close to the rated burst pressure, while other designs may require extra components to withstand vacuum conditions. We just talked about the importance of knowing the operating pressure range for the process so we can choose the right disc design. So different disks have different ability to withstand high operating pressure. The operating ratio is a measure of how close the operating pressure is allowed to be in relation to the burst pressure. Operating ratio of a rupture disk equates to the disk performance under pressure. Operating ratio varies with the disk design or types. Typically, operating ratio of a disk can be from 50 to 95%. The higher the disk operating ratio, the better the disk performance, but at a higher cost. Burst tolerance is the allowable deviation from the nominal burst pressure of the disk. All rupture disks are specified with a burst tolerance. The disk is completely dependent on the absolute properties of the material of manufacture, which has an impact on the burst pressure. This is reflected in the burst tolerance, which allows for these inconsistencies. Tolerance can be made tighter. There are extra testing costs for the maker to achieve a tighter tolerance and at a higher cost also. This slide shows the different tolerance that are specified in European format. We can have a nominal rating with tolerance or state this as a minimum and maximum range. What this gives the user is a fully transparent indication of the expected rupture disk performance. On the left chart, we have a standard tolerance disk with tolerance of plus minus 10%. If the process demands a higher tolerance, we can go to the right-hand chart where we have the same nominal rating, but a tighter tolerance. So what are the benefits of the tighter tolerance?
We can see that here. With any disk, we will always have the red band sitting below the burst rating of the disk. This is the area where the disk should not be operated in normal service. If the operating pressure hits into this area, then the disk should not burst immediately, but it will be fatigued, leading to a low or nuisance burst. If we tighten the tolerance, this can allow the operating pressure to be higher without stressing the disk, and thus helping you to get the optimum service life out of the rupture disk. So let's see how this all fits together. This slide is an example of a simple decision tree that goes through the decisions you must make and the information you need to have to select the correct rupture disk for your new application. I emphasize new because the process is slightly different when troubleshooting an existing application. The first step is to gather all the information you can, both general and specific to your application. Next, you need to get your calculator out and work out the operating ratio required by the application. At this point, you can start to filter out some designs based on the general information you gathered and calculated in the previous steps. It is really a process of elimination. Operating ratio eliminates designs that cannot handle the calculated operating pressure. Fragmentation eliminates designs that don't meet the fragmentation requirement. You should now have a short list of potential designs. At this point, you need to look at more specific attributes of your application and decide on how they affect your shortlist. And again, eliminate the ones that don't comply for one reason or another. Some of the considerations are, is the process medium, liquid, or gas? Eliminate designs that are not suitable for the specified medium. Burst pressure. Eliminate designs that are not available at the desired burst pressure. Size. Eliminate disks that are not available in the specified size. Burst temperature. Eliminate designs that are not serviceable at the desired burst temperature. One last check to make sure you have not overlooked anything, and you are done.
So as a maker, we are not asking the user or even the specifying engineer to make this selection. This is where we can help you. The earlier on the design stage you can involve the disk manufacturer or their channel partner, the better. Only a collaborative disk selection process will result in finding the best disk for the application.
Rupture disk devices are accepted by various national and international codes as a means of protecting a pressure vessel against overpressure. These codes or provide guidance on generally accepted formulas and approaches. Proper sizing of a rupture disk device is as critical as selecting the proper disk design. Undersizing will allow the pressure to rise to unsafe levels because pressure is being generated more quickly than it can be vented. Oversizing is equally dangerous because the device may not open as intended, resulting in a reduced relieving capacity. This is particularly true with reverse-acting disks that require minimum amounts of burst energy to open the disk as designed. There are two recognized sizing methods. The first, known as coefficient of discharge, employs a fixed value known as KB to calculate a theoretical flow rate for a given disk size. This method is also referred to as simple sizing and can be used when the inlet and outlet piping are at least the same size as the rupture disk device. The device is located within 8 pipe diameters of the vessel connection. The length of outlet piping is less than 5 pipe diameters, and the device discharges directly to the atmosphere. ZOOK offers a web-based sizing tool to assist with simple coefficient of discharge sizing. We are going to play a video now to demonstrate some of the features of Z-size.
What you see now is the sizing project. The project is designed to contain one or many individual sizing calculations. The project ID is assigned by the program once I've clicked on Save, and I've also filled in fields to show the project name, customer reference, project date, and some notes. By clicking here where it says Sizing 1, I can begin the first sizing within the project. I'll start by filling in the tag number field by typing in a PSC number. Notice that here on the side, you can now see your tag number referenced. The revision number field can also be filled in with whatever reference you would like, and its entry will append to the tag number displayed on the left. Next, we have a choice to solve for either MNFA or capacity. MNFA stands for minimum net flow area. If you choose MNFA, you can enter the capacity values and the calculator will show an MNFA result. If you choose capacity, you will enter the MNFA value and the calculator will show a capacity result. For this example, we'll solve for MNFA. Sizing code is the next line, and the Z-size offers 3 calculation standards: API, ASME, or ISO. While the required information is very similar, the 3 codes do use slightly different formulas for their calculations, which we will see displayed later in the printout. Next, we can choose the fluid state. The 3 options are gas, vapor, liquid, or steam. The combination of sizing code and fluid state will determine which of the standard formulas Z-size will use in its calculations. All of the calculations in Z-size are based on a sizing method using coefficient of discharge, also referred to as KD. The next line has fields for purpose and relieving case, and the combination of these choices will set the overpressure allowance on the next line. The next line is where we will enter the required capacity. There are several units of measure to choose from depending on the fluid state, gas, steam, or liquid. In this example, I'll use 25,000 pounds per hour. Next, I can enter the burst pressure, which is the set burst pressure of the rupture disk. Clicking here where it says PSIG, you can see there are several choices for pressure units. For this case, let's use 100 PSIG. Here's where we can enter the burst temperature. This should represent the temperature in combination with the burst pressure at which the rupture disk should be expected to burst. Now we can look at the fluid properties. Since we've selected gas as our fluid state, we have a selection of several common gases. Choosing a medium will also show the corresponding values of that particular gas for ratio of specific heats, molecular weight, specific gravity, and density. Now on the right side, we can see the results of the sizing calculation. Since we're solving for MNFA in this example, Z-size has calculated the required MNFA is 3.876 square inches based on all of our information entered in the left pane. In the unit of measure dropdown, you can also choose centimeter squared or millimeter squared. Here, by equivalent diameter, the calculation is simply converting the MNFA in area to its equivalent diameter. In this section called Enter Disk Specs If Known, we are giving you the opportunity to enter the MNFA of your own rupture disk, and Z-size will calculate the resulting capacity. Calculation is using all the information that's been entered on the left side. So if I enter 5 inches squared, the calculation result is 32,247 pounds per hour. Here again, we have the drop-down fields that give some flexibility to enter different units of measure. Next, I'll show you how to add, copy, or delete individual sizing within a project. Over here on the left at the top, you'll see two icons. The first is a plus sign that simply adds another sizing to the project, and the second icon is for copying a sizing. If I click on the copy icon, we now have a line that is an exact copy of the first one. Here we can change any of the fields to evaluate the impact on the size calculation. For example, I'll change 25,000 pounds per hour to 30,000 pounds per hour, and the resulting MNFA changes from 3.876 to 4.652. Here at the right top corner of the screen, you'll see icons for print, save, save and exit, or exit without saving. If I click on Print, ZSize will generate a calculation sheet with the information from your sizing entries and the results. It will open on a separate tab in your browser, and from there you can select your print options. Now I'll click Save and Exit, and that will bring us back to the main screen. Here we can see that your sizing project has been saved to the database. At this point, if you're finished, you can log off or simply close your browser, and your sizing project will be saved for the next time you log in. Thanks for watching the video on ZSize. Please contact ZOOK if you have any questions regarding ZSize or your rupture disk application.
Awesome, right? ZSize is a great tool that can be accessed by anyone from a link on our website. Please give it a try. The second sizing method is resistance to flow and differs from coefficient of discharge because it considers all piping components in the relief system. The Kr value of each component is added to develop a total K value for the system. The system K is then used to calculate the capacity of the entire relief system. Sounds simple, but a complete knowledge of the full relief system is a must. Typically, this method is used when the coefficient of discharge method does not apply. Caution should be taken when selecting rupture disk designs based solely on a low Kr, as this can lead to a small diameter relief system with limited options to correct the value if changes in disk or pipework design are required in the future. Vendors can offer useful advice and sizing assistance, but ultimately, the responsibility for sizing lies with the end user. The takeaway here is that right sizing is the goal, which requires collaboration between the user, process engineer, and the disk manufacturer. Ben mentioned earlier an application that includes a rupture disk device in combination or in series with a pressure relief valve. For this application, the sizing is based on the pressure relief valve capacity. The effect of the upstream rupture disk device is accounted for by applying a default 0.9 combination capacity factor, or CCF, to the valve flow capacity to give a conservative relieving capacity for the combination. A certified CCF for a specific disk and valve combination can be derived by actual flow testing. This will typically give a higher CCF, meaning a lesser derating of the combination. Caution is advised not to rely on a high certified CCF value. Doing so will limit flexibility if changes to the rupture disk or pressure relief valve are required in the future.
We have discussed the fundamental selection and sizing of a rupture disk. Now, let us look at another important aspect of the device, troubleshooting. It is important to remember that a rupture disk is a device that is designed to burst. Some people say designed to fail. We like to say designed to burst or activate at a specified pressure. Just like any other engineered mechanical device, things can happen, and that will affect the disk performance, and this is when this manufacturer have to use some detective work. First and foremost, rupture disks will not last forever. They are mechanical devices exposed to various forces, temperature, and other process conditions, and therefore they can fatigue. So bursting low may simply be a case of continued exposure to demanding service conditions. Why do rupture disks fatigue? The reason is that by design, there is no way to build in extra strength to the disk to allow for corrosion and loading. This is both a blessing and a curse, as the lack of over-design, what would normally be considered as safety factors, is at the heart of the rupture disk function. It is also what will give the disk a limited service life if the service conditions are demanding. This is why the disk maker should be your partner in evaluating the process and selecting the right disk from the start. Rupture disks are engineered products. They can be delicate and fragile, especially with reverse acting disks. Any minor damage to the disk dome will negatively affect performance and cause the disk to burst or collapse low. All disk manufacturers will take extreme care to fabricate, package, and ship you their disks in good condition. But handling in the field is just as critical. This should always be handled by their agents or techs. Never touch the disk dome. If a disk shows any sign of damage whatever so, it should never be installed. Please consult the maker. This damage in the field is the single largest cause of nuisance burst. I use the term nuisance burst loosely, and what I mean is a burst at a level lower than specified or expected. Nuisance bursts are expensive and result in significant loss of product or time or both, so they need to be avoided. We had a situation a while ago whereby a client contacted us because they were having performance problem with the competitor's product. Namely, they were experiencing nuisance bursts. Adding to the base problem was that their equipment was very remote and unmanned. Every time they had a burst event, they had to send a crew out for an expensive repair. They simply thought there was an issue with the disk design and performance. It turned out that in order to reduce costs, the inlet side of the holder had been reduced to a point where the disk dome protrudes beyond the holder face, similar to the assembly shown on the left. This can create problems during installation, as it is easy for the dome to be impacted during handling and insertion to the assembly between flanges. This can go undetected until it results in service issue, and this is what was happening. Our solution shown on the right was simply to provide an assembly with similar disk style, but with a pre-top holder that seals the disk and fully protect the dome. The problem was solved, and we have a happy customers. It is important to realize that a rupture disk assembly is typically another joint or connection point in a pressurized system. All rupture disk manufacturers have recommended both top for their design, and following this recommendation is critical to achieve a leak-tight connection. Some disk designs are extremely torque sensitive, and over or under torque can cause leak damage or leakage. Most rupture disk assembly utilize gasket to seal the device into the piping, so gasket style and, more importantly, gasket integrity is critical in ensuring a proper seal. The disk itself is normally sealed in the holder using a metal-to-metal seal, so gaskets are not required within the holder. Misaligning holder and disk component or incorrect torque pattern can also create leaks. Similar to any tightening process, it is important to gradually increase the torque around a flange in order to provide equal loading to the assembly. Misaligned pipe like that shown in this picture or incorrect flange torque can result in multiple leak locations across a rupture disk assembly. Some manufacturers offer pre-top holders which allow the installer to preload the disk and create a leak-tight assembly prior to field installation. There are various methods used to seal the rupture disk within the assembly. This varies from manufacturer, but can include O-ring, pinch point, weld, and metal pipe rings. Care should always be taken when handling holders, sealing surfaces, and they should be inspected every time a disk is changed. Any damage to a sealing surface can cause leaks. In this picture, you can see that the raised sealing bight section of the holder has been damaged, which could create a leak path in the assembly. Not all holders or disk assembly are suitable for every situation. If you are having a leakage problem and you are confident that your disk and holder sealing surfaces are not damaged and that you are following proper installation instruction, then you should contact your disk manufacturer for help. So if you do have a problem, we want to help you. And in order to fully understand the issue in hand, we need detailed information from you. Firstly, we need the lot number of the affected disk or disks. All manufacturers use lot number to identify manufacturing badges of product. This number gives us access to every aspect of the disk manufacturing history and is critical for investigative work. What else? The installation history at hand. Is this a new or existing installation? How long has the disk been installed? Have any of the process conditions changed? Do you have similar issue in the past or specific to this recent shipment or product? Take plenty of pictures, the disk, holder, flange setup, upstream and downstream. All this information builds the picture in diagnosing problem and finding engineering solution. All these manufacturers will have a quality and technical support team available to help you. They will all take performance issue with your respective products seriously. We are all in the business of making safety product and we take that responsibility very seriously. However, do understand that remotely analyzing or forensically diagnosing performance problem is difficult for this manufacturer to do alone. We need your help. It's rarely the disk fault. It is a mechanical device simply reacting to its environment. And it's up to all of us to work out the best engineered solution when a problem arises.
People ask us all the time, how long will my rupture disk last? The truth is nobody knows, and scheduled preventative maintenance is recommended. Or if the process is down, take the opportunity to change the disk out. In absence of actual installation history, we suggest starting with a 1-year interval between scheduled disk replacements. We understand how self-serving this sounds, but it is better to have proactive preventative maintenance. The cost of replacing a disk is far less than the cost of an unplanned shutdown and the resulting loss of product and production. There are no specific maintenance tasks that can be performed on a ruptured disk device. If a metal ruptured disk device is taken out of service, then it should be replaced unless it is assembled into a pre-torque holder. Pre-torque holders with integral pre-torque bolts can be removed from service, inspected and reinstalled safely because the seal between the disk and holder is not disturbed. Holderless graphite discs can be reinstalled after inspection. During this replacement, personnel can perform maintenance tasks on the ruptured disc holders. First, the holder's gasket surfaces should be examined for foreign material. Any adhered gasket material from the previous installation should be cleaned from the gasket surfaces of the holder thoroughly. Dirt and grit on these surfaces can cause leaks. Next, the seat area should be inspected for scratches, dents, or nicks, because imperfections on these surfaces can also cause leaks. Care should be taken not to introduce any new scratches into the seating surface. A clean cloth with a suitable solvent can be used to remove residue. If that does not fully remove it, fine emery cloth or steel wool can also be used with caution not to damage the surface by pressing too hard and making grooves or scratches into the sealing surfaces. If scratches, dents, or nicks are present, contact the manufacturer. Never machine or modify the holder. The geometry is critical to the disk performance. In summary, prevention is always better than cure. Be ahead of the game and keep your process team happy and your people safe by being proactive with a defined maintenance and change-out regime. In closing, all ruptured disk manufacturers offer good quality products that will work as intended, provided they are selected, installed, and applied correctly. We need your help to ensure this all happens. Thank you for listening.
Thank you, Yip. I also want to thank all of you for your time today. I hope we managed to increase your understanding of ruptured disk And to echo what Yip has just mentioned, a collaborative effort between yourself and your rupture disk manufacturer will ensure a proper size and engineered solution for your pressure relief requirement. Thanks again.
Thank you, Ben and Yip. That was a great presentation on rupture disks. We now have some time to answer some questions that have been sent in during the course of this webinar. But before we just go into those, I just want to remind our audience that the Z-Size program that we have on the ZOOK website is available to use for your sizing requirements. And this is a fabulous piece of software to use with a printable output. And there is tutorials that will allow you further tuition to be able to understand how to use it. So just wanted to remind our audience of that. Now I'm looking at the list here. We've had some very good questions coming in. The first one I want to put to Ben. So what is a vacuum support for a rupture disk and how does it work?
Okay, vacuum is a common process condition. Remember that rupture disk is a differential device and vacuum represents a reverse pressure differential. So most of the high performance rupture disks can handle vacuum by design without having additional vacuum support. However, some design may require adding a vacuum support immediately below the disk membrane. This is to support and protect the disk from damage from when there is a vacuum.
To add on what Ben has added, in many cases, the vacuum support would not fully open together with the disk, which means the disk flow area will be reduced and the resistance to flow coefficient or the Kr value will likely be higher. Even in a fully opening case of where the vacuum support opens up completely, we tend to believe that there will be some restriction to flow nevertheless. Hope it answers the question, Richard.
Great, thank you very much, Yip and Ben. Looking at the next one that's come in, I think I could even probably answer this one, but I'm going to ask Yip to do that. Do all rupture disks require a holder?
Thank you, Richard. No, not all disks will require a holder. For instance, most graphite disks are holderless. We have some metal disks that will fit directly between companion flanges. However, these disks are mostly limited to low pressure applications. For high pressure applications, we will require high performance disks that would work better with a holder. By using a holder, we could actually control the critical geometry of the envelope around the disk transition radius so that it can be well controlled. On top of that, the holder will also protect the disk dome during installation. Thank you, Richard. Okay.
Just looking at an interesting question that's coming in now, which I think actually is very interesting. We all know that rupture disks are there to be used as a form of pressure relief device, and I think everybody feels and understands that to be positive pressure. But can rupture disks be used as a vacuum breaker?
Okay, Richard, I'll take that question. The short answer is yes. The disks are only reacting to a pressure differential. So by fitting a suitable rated disk inverted, it will act as a vacuum breaker. So this option also allows the disk to be operated as low as in the millibar level. And it is also possible to engineer the disk to operate both in the positive and negative vacuum pressure relief. This kind of disks, they are dual rated. The dual rated pressure disks are quite specialized and they are a great solution for tank protection. Hope I answered the question, Richard.
Okay, very good. Thank you, Ben. Sort of hot on the heels of that last question, the next one is, what does it mean when a disk is fail-safe?
Okay, Ben here again. A fail-safe disk will burst at or below its rated burst pressure, even if it is damaged or incorrectly installed. So that's the term used for fail-safe. This can include incorrect orientation of the disc relative to the flow direction also. Gib, you have anything to add?
Yeah, I think it would be safe to say that a fail-safe disc should also have a reversal ratio of less than or equal to 1, as well as a damage ratio, or some call it the safety ratio, should also be less than or equal to 1.
Yeah, just to add on, actually, do note that not all discs are fail-safe, actually. For example, reverse acting disc or disc with the vacuum support. That's why it's essential that anyone that is installing rupture disc need to understand the importance of how a disc is correctly installed. And most rupture disc manufacturers offer training for plant personnel to do the installation of rupture disc.
Okay. This next question has actually come up on a few occasions looking at the list in front of me here. Yep, I'm going to put this one to you if I may. What temperature should be used to identify the specified burst temperature?
The burst temperature should be specified at what we call the coincident temperature that the disc will see during burst or relief. This is because the burst pressure has an inverse relationship with the temperature, which is to say it will burst higher if the temperature is lower for a disc with a given rated burst temperature and pressure. This is actually a natural function of material properties, because the disc membrane material will become weaker at elevated temperatures. Having said that, there will be a difference between different materials towards the sensitivity of the way they respond to the temperature. Ben, could you have anything to add on?
Okay. Usually the burst temperature is specified by the process engineer. And like what Yip just said, they should look at the temperature where the disc see in the burst scenario. So if you are in doubt, the safest way to rate the disc burst temperature is to use the lowest operating temperature. Then the disc will burst low, even if you see a higher temperature. And there are also materials like inconel and nickel that are less temperature sensitive. They are good material you can use if you are not really sure of the burst temperature, because it covers a wider range, not so much of a temperature sensitive to it on the pressure. Okay,
right, very good. I recognize the person who had actually sent in this next question. That's an old friend of ours, friend Benny from Singapore, by the looks of it. Yep, Benny has asked this question. So how close is the burst pressure of the rupture disc to the set pressure of the relief valve when it's installed upstream of it?
This is Yip here, Richard. There are two ways where the rupture disc can be used in combination with the pressure relief valve or the PRV. In the context of the question, the rupture disc would be used in series and located at the upstream of the PRV. Ideally, we would like to set the burst pressure of both the rupture disc and PRV at the same level, so that they will open together when overpressure occurs in the system. If the rupture disc burst pressure is lower than the PRV, which would mean that there's a possibility that the valve would remain closed when the rupture disc bursts, thus exposing the relief valve to the process conditions. If this situation prolongs, it may lead to corrosion in the relief valve because it is no longer protected by rupture disc, or even lead to a fugitive emission of toxic gases or vapors, or loss of valuable product or production, because the pressure relief valve is essentially a spring-loaded device and is not 100% leak tight. For the case where the rupture disc is rated higher than the pressure relief valve, we have to take extreme care so as not to set the pressure higher than the maximum allowable working pressure, the MAWP, of the pressure vessel, which the rupture disc is served to protect. It will also be a violation to the ASME or the European PED code. Normally, there should be no reason to rate the rupture disc at a higher burst pressure than the pressure relief valve. Thank you.
Okay, great stuff. Yep. This is a topic which actually we've mentioned a little earlier, but it's a question we get asked not only today, but regularly from our client base. Ben, what is the shelf life of a rupture disc?
Okay, yeah, this is a good question. And in fact, like what you say, you know, a lot of people ask us about this question. Here are a few important considerations about the shelf life. Many rupture discs are shipped in boxes, and it's not uncommon for them to be individually boxed. So the best practice for storage would be to leave them in the box they arrive in. And the box actually provides protection against the environment elements, as well as certain degree of drop shock protection. Yip, you got anything else to add on it?
Yeah, please always handle the disc with care. Some discs may look big and bulky, but the truth is the metal foil from which the disc membrane is made is typically less than 1 millimeter thick. So it is more fragile than it appears. Bear in mind that a rupture disc is a precision instrument, which means if it is damaged, it may burst out of specs. And it can be catastrophic if it bursts beyond the upper specs limit and beyond the MAWP of the pressure vessel. If you have to remove the rupture disc from the box for inspection, always handle along the perimeter of the disc and use the disc tag as the support. Avoid touching the disc dome, and it is a critical to function parameter.
Okay, maybe I'll add on a bit on this. Some rupture discs utilize Teflon liner. So this liner could be for protection of the disc from corrosive media, or they could be an integral component to the proper opening of the disc in service. So this liner can be affected by temperature changes, causing them to expand or contract. So we do recommend that rupture discs be stored in a climate-controlled environment. If a disc is stored properly and protected properly, then it has an almost indefinite shelf life. Actually, hopefully you are already employing some of this technique, but if not, now is a good time to consider the changes needed to better protect the shelf life of the disc you have in storage.
Okay, well, thank you very much, Ben. Just looking at the time we have here, I think this is probably going to have to be our last question in this Q&A session. Thank you to everybody that's contributed to these. The final question here that I have is, what is a pre-torque holder?
Okay, Richard, I'll take that question. A pre-torque holder is equipped with a high-strength recessed cap screw, which actually holds the device together. So with enough clamping force to properly engage the butt into the disc material. And a pre-torque holder would dramatically increase the potential of a successful installation. It also allows for the removal, inspection, and replacement of the complete disc and holder assembly without disturbing the bite seal. Hope that's the answer the question.
Thank you very much, both Yip and Ben, for your answers there. We are approaching the end of our allotted hour for this webinar. I'd like to thank Ben and Yip for sharing their experience and their expertise. ZOOK is a leading manufacturer of high-quality metal and graphite rupture discs and other pressure relief products. The webinar will be archived for future viewing on our website and our YouTube channel. We'll also send everyone the video and slides in the next couple of days. Thanks to all the viewers today. Goodbye.